In 1949, a Department of Defense study group selected Cape Canaveral as America's first long-range missile test facility. The Cape was primarily undeveloped land when the Air Force began building. Here, missiles launched eastward could take advantage of the Earth's 1,100 miles an hour easterly rotation. The area was acquired at minimal cost, and there were important range safety features. Facilities could cover more than 20 miles of coastline, minimizing damage in the event of mishaps. There would be no flights over populated areas, and two broad rivers between Cape and mainland formed a natural maximum safety zone. The flat terrain meant no obstacles for instrumentation systems, and Weather Bureau records showed excellent weather conditions, 360 flying days a year, plus the fact that the eye of a hurricane had never passed over the Cape. All these factors added up to an excellent range potential. The Air Force Eastern Space and Missile Center was born with a slab of concrete, painter's scaffolding, sandbags, the latest radar equipment available, and a few cinetheodolites and cameras. In July 1950, the first launch test involved a captured German V-2 modified with a WAC Corporal second stage named Bumper. It was the first in a string of successes, punctuated by occasional failures as research and development testing progressed. The Lark was one of the earliest. Matador, forerunner of a series of cruise missiles. Snark, Mace, Beaumont, Navajo, Redstone, Thor, Atlas, Titan, Minuteman, and the Navy's Polaris, Poseidon, and Trident. The ETR also supported NASA programs with Air Force-developed boosters. Atlas Centaur, Thor Delta, and Titan Centaur. In growing to test each improved vehicle, large and small, the range acquired the ability to reach into deep space. Over the past 30 years of R&D testing, many changes evolved. At one time, Grand Bahama Island was the most distant downrange station, 150 miles from the launch site. But soon, others were needed. Currently, Grand Bahama, Antigua, and Ascension Island are major island tracking installations which comprise the range. Since its inception, the assigned mission of the range has remained constant: to provide facilities and support services to launch and test missiles for the Department of Defense, NASA, and friendly foreign governments. Our main launch activity occurs at Cape Canaveral Air Force Station. Cape resources include many launch facilities, both large and small. Sites no longer in use can be reactivated, and there's room for totally new installations, such as a multi-million-dollar complex at the tip of the Cape, housing checkout, testing, and operations of the Trident II missile systems. In the industrial area, hangar and office space is available, with buildings for storage, assembly, and testing of items of all sizes and descriptions. There are facilities for indoor testing of sensitive components and storage areas for hazardous propellants and other chemicals, as well as fully staffed facilities to help solve technical problems. Long-range weather forecasts are continuously updated along with day-to-day forecasts. Range communications media include high-capacity submarine cables to and from Antigua Island and an assigned spectrum of radio frequencies, including satellite relay capabilities and customary hardwire modes. With its own flight control tower, the skid strip handles the largest air cargo transports. Contractors supplying rocket components from entire stages to the most delicate satellites and test equipment often prefer direct flights to the Cape. This avoids potential hazards of prolonged land or sea travel. For an illustration, the Army uses the Cape for the operational testing of its Pershing missile systems. After being flown directly to the Cape from Europe, missiles and launch equipment move to the launch site. Crews then go on standby alert status until surprise firing orders are issued under simulated combat conditions. Ships of all sizes can dock at Port Canaveral at the south end of the Cape. Range instrumentation ships and Navy support vessels make this their home port. Fully equipped, they can collect telemetry, optical, and radar data from stations anywhere on the 7 seas. They afford a wider choice of test flight trajectories by filling gaps between land-based stations. The nearby submarine turn basin is another unique facility at Port Canaveral. Channel dredgings enable it to accommodate the nation's largest submarines. In fact, the long wharf can dock 2 vessels at a time, while the elevated mobile crane loads the largest Trident missiles on board. Locks at the west end of the port give shallow draft vessels access to the Banana River, and a barge canal cuts across Merritt Island to the intracoastal waterway. The key to successful R&D testing lies in prompt acquisition of accurate metric, telemetry, and electro-optical data. Program requirements dictate whether needed information can be obtained from a single source, 2, or all 3. The range collects all 3 primary types of data. Metric, using spatial measurement to determine flight path. Telemetry, with information measured on board a vehicle transmitted to a receiving site, and electro-optical observations recorded on film or videotape. There are 4 sources of metric data. Optics, giving azimuth and elevation angles. Target tracking pulse radars, which yield range in addition to angles. Navigation location systems, which give geographic position of ships at sea. And acoustic impact location systems for determining the geographic positions of bodies re-entering the atmosphere. The MILS, Missile Impact Location System Target Array, is an example of the latter. Sounds from a splashdown are picked up by a pentagon array of underwater hydrophones. Mid- and long-range target arrays are established near our downrange stations at Antigua and Ascension. The FPS-16 radar near the skid strip can range out to 1,000 nautical miles under favorable conditions. 2 mobile C-band radar systems provide safety support by triangulating missile location during early flight. From this location, MCBRs have line of sight to the missile and track manually to a 15-degree elevation. Then the automatic skin or beacon tracking system takes over. The on-axis FPQ-14 radar at Patrick is known as the MIPR, Missile Precision Instrumentation Radar. The MIPR represents one of the largest radars on the center, with a tracking limit of 32,000 miles. By combining solid-state hardware with components tied to advanced computers, on-axis radars return precision data in near real time. Easily star calibrated, they provide highly accurate data. On-axis systems are available at Patrick Air Force Base, Grand Bahama, Antigua, Ascension, and on Merritt Island. All these radars send important real-time data to range safety. A range safety officer is on duty during every launch to ensure that no flight deviation can endanger either life or property. In addition to closed-circuit television and real-time verbal reports, he relies on 3 computer-generated electronic displays. One of these is the impact predictor. It has a map outline and shows the intended flight path flanked by safety limit lines. Moment by moment, it shows where debris will impact if it becomes necessary to end the flight. Other displays can be called up to show azimuth, elevation, and telemetry information. At liftoff, data from these radar systems is fed directly to the Cape. The cyber computer in the Central Computer Complex system combines these radar inputs and delivers them instantly to electronic displays, which are the prime input to the range safety officer's decision-making responsibility. Our 3 island tracking stations are the backbone of the Eastern Test Range and vital in performance of our mission. These stations are unique settlements in themselves. This is Grand Bahama Island Station, known as GBI. Each one is like a small city, virtually independent of the local economy. GBI, about 60 miles east of Palm Beach, Florida, also has a range safety command destruct capability. This is the island station closest to the Cape. The farthest island station is Ascension, a volcanic mountaintop rising in the middle of the South Atlantic. A British possession, Ascension is roughly 7 miles in diameter and lies about 5,100 miles from the Cape. A 10,000-foot landing strip is regularly used to airlift supplies and personnel. The alternate contact with the outside world is this minimum docking facility, limited to shallow draft vessels. The main base has all the features of a small city: housing, distilled water, electric power, and dispensary, among others. The barren cinder-covered hills offer ideal locations for a variety of instrumentation to record the signals of vehicles re-entering the atmosphere. The TTR, or Target Tracking Radar, and the TAA-3 telemetry dish are typical of the instruments gathering data on Ascension. Several systems are involved in returning downrange data to the Cape. From as far as Antigua, clean data, free from interference or background noise, is sent back by underwater cable. Ascension, on the other hand, relies on satellite links and high-frequency radio. Original data recordings also returned by the quickest alternate means to provide a backup. Telemetry supplies information on the internal status and operation of test vehicles. Information such as engine or skin temperatures, fuel flow rates and cutoff times, stage separation, and many other events are vital in R&D evaluations. Onboard transmitters speed this information to ground receivers. The smallest receiving antenna, 7 feet in diameter, is also the largest airborne telemetry dish. It's mounted aboard the Advanced Range Instrumentation Aircraft, ARIA, which may be called in on tests requiring their special capabilities. The largest receiver is the 85-foot on-axis computer-controlled parabolic antenna at Grand Bahama. The Advanced Range Instrumentation ship Redstone carries 4 30-foot telemetry antennas. In addition, each downrange station has one or more of these important systems. At Tel 4 on Merritt Island, there are 33-foot and 24-foot auto-tracking telemetry antennas. Antigua has a dual telemetry installation with a 33-foot and an 80-foot signal collector. These powerful receivers minimize onboard power requirements for signal transmissions. On certain small test projects, optics instrumentation is the only required resource, but the range is prepared to obtain optic data from tests of every magnitude. The largest mobile system is IGOR, also known as MITS, Mobile Instrumentation Tracking Telescope System. The lens has an 18-inch aperture with a variable focal length from 180 to 500 inches. Permanently mounted in elevated domed observatories are the ROTI, the acronym for Recording Optical Tracking Instrument. Its telescope has a 24-inch aperture and a 500-inch focal length. The 48-inch ITEC south of Patrick is a unique telescope system. Using on-axis drive, it can track a Cape launch or a satellite in orbit. A mobile optical tracking system, or MOTS, carrying up to 4 cameras, combines infrared and television remote control. It can be placed within a restricted zone close to the action, but without endangering the operator. The Swiss-built Contraves records a target image plus azimuth and elevation data. Generally, 3 or more are used for triangulation purposes. Shielded cameras provide close-up studies of detailed action. Timing is the key to correlating inputs from all these diverse data sources so that a complete history of each test emerges. Pulses originate from an atomic clock corrected to microsecond accuracy with the U.S. Naval Observatory. During a test, the timing on all data is recorded simultaneously in increments down to 1,000th of a second. In this way, thousands of bits of radar, telemetry, and optical data are accurately matched within a single chronological story. Generally, raw digital or analog data is received on magnetic tape, on various types of film, and on other media such as punched paper tape and cards. All these are converted to computer format, then processed as required. The prime data reduction computers include the system in the technical lab at Patrick, plus the real-time computers at the Cape when they're not involved in launch-related demands. Center experts have created an advanced level of processing techniques to assure that maximum usable information is developed from the raw data inputs. The results are produced in any format and medium required by a range user. But the range isn't just an array of mechanical and electronic devices. It's made up of highly skilled people who make certain that these resources are used effectively. The blue sitters, civil servants, and contractor employees have set a record which speaks for itself. Industry and civilian neighbors welcome and support the range operation admirably. The Air Force has built a superb test range and proven its capability to support tests of the largest as well as the smallest of devices. Even tracking a small tactical surface-to-surface missile like this one, the Penguin, wasn't beyond the capability of the range. In spite of Penguin's small size, short range, and low trajectory, the range still supplied 100% successful support. Any portion of these advanced resources is at the command of potential users who require a test site. Because this complex facility is in full operation, important cost savings are available. Experienced personnel have developed efficient procedures for conducting thousands of tests of all types and are ready to provide the services users may require. Not content to remain with the status quo, the range is constantly striving to upgrade and improve its already proven technology to meet new challenges of the increasingly complex missile systems being tested on the range. At Patrick Air Force Base, headquarters for the range, Eastern Space and Missile Center personnel are hard at work planning for new instrumentation systems and facilities. These will not only enhance our support posture, but will enable us to perform our mission in a more cost-effective manner. A few of the other improvement and modernization projects, either in planning or implementation phases, include a new state-of-the-art instrumentation facility being added about 95 miles south of Patrick at Jonathan Dickinson State Park. Equipment from the range's deactivated Caribbean tracking station at Grand Turk will be used, including a radar antenna, 4 telemetry units, command and flight test support systems, and a microwave relay to the Cape. The new facility will become operational in 1987. It'll be essential in support of the Navy's Trident II missile systems, among others. The improvement and modernization program also includes updating the existing telemetry at 4 sites, as well as changing over to SATCOM to meet the growing needs of future users. Phased array radar now being planned for the Cape will enhance our ability to track multiple trajectories, covering more targets more accurately, both at greater speeds and greater ranges. Other work includes consolidating the Range Control Center, the Central Computer Complex, and the Communications Facility into a Test Operations Control Center. State-of-the-art planning along this line would take us well into the next century. Furthermore, improvements like this would add to our capability in supporting future space programs of the highest national significance, such as the Small ICBM and perhaps the Strategic Defense Initiative. Full utilization of the Eastern Test Range benefits both its present as well as prospective clients and assures the United States of maximum returns at minimum cost from its investment. That's important to us and to you.
Little League. Baseball is a favored recreation throughout the Cape Kennedy area. There's a nearby game underway almost every evening of the spring and summer. Here, midway between Patrick Air Force Base, headquarters for the Air Force Eastern Test Range, and Cape Kennedy, America's best-known launch site, the evening traffic flow is normal. As is customary, quite a number of families have succumbed to the lure of gourmet dining in one of many fine restaurants in the area. Several couples, awaiting their turn to dine, are enjoying a few moments in the lounge, aware that a launch is scheduled for this evening.
Coming up on T-minus 30 seconds and counting on my mark. Mark, T-minus 30 seconds and counting.
Stand by for terminal count.
Stand by for terminal count.
10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Mission confirmed.
Roger, wire.
TM confirms all engines go.
Lift off. Roger, wire. Understand, lift off. Roger, TM. All engines go.
TM shows program downrange.
Roger, TM.
VPs are green.
Wire green. Roger, wire. Roger, VP.
Picking up excessive pitch on TM.
Roger, TM. Excessive pitch.
Radar on the nozzle. TM jet solid.
Roger, TM. Understand, yes. IP is left of nominal, about 10 seconds slow at this time, moving downrange. IP is starting to move back towards the Cape.
TM confirms missile erratic, excessive pitch.
Roger, spinning arm, spinning destruct.
The mission of the Air Force Eastern Test Range is to provide the facilities for launching this nation's space vehicles and to provide for the protection of lives and property from errant missiles. Even though today's boosters are reaching high levels of reliability, as commander of the Air Force Eastern Test Range, I must still prepare for a small percentage of failures. From the very beginning, one of our principal concerns has been range safety. The first launch from Cape Kennedy, then called Cape Canaveral, was July 24, 1950. It was called Bumper, a German V-2 rocket with a Watt Corporal second stage. Support equipment was primitive and makeshift. But the means for stopping an errant missile was not left unattended. A command-controlled strut package was provided so that a radio signal sent from the blockhouse would stop the missile in flight. The Army-sponsored Bumper test was a complete success. Today, because of the enormous potential of modern boosters, there is considerably more to the business of safety. To show how range safety fulfills its responsibilities, let us follow the preparation that goes into the launch of the Air Force's most powerful space vehicle.
This is the Titan 3C, the 14th to be launched from the Air Force Eastern Test Range. It stands 128 feet high and develops 2.5 million pounds of thrust at liftoff. Its payload, 2 Vela nuclear detection satellites, to be placed into separate precise orbits by the highly sophisticated booster system. But the story doesn't begin here. Planning for the flight began about a year before the launch. Once the decision was made to launch the Titan, the launching agency, the 6555th Aerospace Test Group, brought details of the mission and the proposed trajectory to range safety. Under the chairmanship of the Director of Range Operations, Range Safety meets with members of the range support agencies and the Test Group Titan project officers. In order to receive flight approval, certain stringent range safety requirements would have to be met. The space vehicle, for example, would have to accomplish its mission within specified launch azimuths. The boosters would have to carry approved electronic decoders to receive the range safety command for destruct should the need arise. Radar transponders on the missile would have to meet precise specifications to ensure positive tracking throughout the flight. After reaching initial agreement as to what is expected, mathematicians start the intricate work of deciphering trajectory information. Programmed into the IBM 36065 and 7094 computers are basic data about weight, thrust, burn times, stage separation, and other factors. Eventually, questions concerning range safety will be answered. For instance, on the azimuth and trajectory requested, will a spent stage impact in a Caribbean island, a distant shipping lane, or in Africa? The answers to such questions are critical considerations in establishing final approval of the flight. While the Range Safety Office and the test group are resolving the details of launch approval, assembly of the space booster begins. The stages of the core vehicle arrive by cargo plane. Offloaded on special transporters, they are carefully moved to the assembly area. Segments of the rocket motor boosters arrive by rail and are readied for the assembly procedure. Inside the vertical integration building, the liquid-fueled three-stage core vehicle is erected directly on its mobile launcher. The multi-burn third stage, called the trans-stage, serves as a switch engine in space and is what makes this booster system so versatile. Its stop and restart capability makes it possible to place as many as 8 payloads in different space orbits. From the vertical integration building, the fully assembled core vehicle is transported by 2 diesel locomotives to the solid motor assembly building, the last assembly point before the launch vehicle reaches the pad. Here, solid rocket motor segments, each 10 feet in diameter and 10 feet high, are in process of assembly prior to being attached to the core vehicle. The completed booster leaves the solid motor assembly building on the final leg of its journey to the launch site. The 2 solid boosters, 85 feet high, carry the core vehicle and payload to an altitude of nearly 25 miles before they burn out and are jettisoned. At the spin test facility, while the launch vehicle is being prepared, each of the 2 Vela satellites are dynamically balanced and tested for structural integrity. This is the final spacecraft checkout before transport to the launch pad, where it will join the waiting Titan 3C. With the Titan at the launch pedestal, pad safety prepares for the more hazardous of pre-launch operations. Final checkout of the redundant command-destruct system begins. In addition to explosive primacord installed on the solid propellant stages, wafer charges are mounted within the liquid propellant core vehicle between the fuel and oxidizer tanks. These explosives are attached to pyrotechnic squibs, the key link in the destruct system. Should the range safety officer need to destroy the space vehicle, the explosives will be fired by the squibs when either one of the 2 command control receivers receives the destruct signal. With the ordnance installation completed, the command destruct system is go. Another, and potentially the most catastrophic of pre-launch operations, is the fueling of the vehicle. Nitrogen tetroxide is the oxidizer, Aerozine 50 the fuel. The Titan 3C carries 300,000 pounds of these hypergolics, by far the largest amount of this type of propellants loaded by any United States missile. They are hazardous not only because of their incendiary and explosive potential, but because each is highly toxic to man. Protective clothing worn by handlers insulates them from splashes or fumes. As demonstrated in the laboratory, the propellants have the additional advantages of being shock-proof and storable, as well as yielding a high specific thrust. That is, high thrust per pound of propellant per second. And most significantly, they ignite on contact. In the vertical integration building, an important coordination effort is near completion. From the onset of launch preparations, the Range Safety Officer, or RSO, has been learning every aspect of the vehicle, its components, its operations, its systems, and its various idiosyncrasies. In addition, he has gone through repeated procedures drills with computerized simulations of liftoff and flight. By launch time, he will have a comprehensive knowledge of the Titan 3C, as well as quick response reactions to flight variables which might occur. After flight trajectories have been finalized and launch conditions approved, the RSO discusses with the mathematicians of the Flight Analysis Branch the preparation of the range safety destruct charts. Utilizing the answers that were compiled by the larger computers, smaller computers develop criteria upon which the range safety officer can make his decisions. On various overlays, destruct lines are drawn. These lines are based on expected winds at launch time, velocity imparted to pieces by explosion of the destruct charge, missile velocity, maximum turning rates, survivability and ballistic coefficients of re-entering bodies, and the range safety officer's reaction times. The results are precisely calculated boundaries that protect land masses such as the United States mainland, the Caribbean island chain, South America, Europe, and Africa. On the charts, two kinds of trajectory information are plotted: the actual vehicle position in space and the instantaneous predicted impact points on the surface of the Earth. Should the missile veer off course and the predicted impact point reach a flight termination line, the message to stop the flight must be sent by the range safety officer. The CDC 3600 computer is used to overcome the complex mathematical problem of calculating this trajectory information and presenting it to the range safety officer instantly. The most critical part of the launch in terms of safety is in the launch area, because approximately 90% of all missile failures occur soon after liftoff. During this period, the RSO relies on several charts, such as close-in impact prediction destruct lines. Immediately after liftoff, the difference between a safe nominal missile and a catastrophe is just a fraction in terms of time and distance. Another important display for the RSO is the vertical plane, or VP chart. This provides him with a different type of destruct criteria during the critical moments of early flight. The responsibility of the RSO at this time is made even more burdensome because he must not only solve the problem of protection, but must also allow the missile the maximum permissible opportunity to fly and achieve its mission. A chart of present position deviation lines is a third source of information for the RSO. The sensors that support the range safety officer are varied and numerous. Television provides both flight line and program view of missile flight. Not the least important is the wire sky screen, which, despite its simplicity, provides valuable information in the first few seconds of flight before radars can positively acquire. 3 radars are located on the mainland, and 5 others downrange as far as the island of Antigua. Typical of range safety radars, designed specifically for missiles, is the Patrick MIPR, Missile Precision Instrumentation Radar, with a 29-foot antenna which can track with precision a space vehicle 60,000 miles in space. Downrange, as well as on the mainland, telemetry receivers provide such data as thrust chamber pressures, yaw pitch and roll rates, destruct receiver sensitivity, and staging events. Telemetry antennas at the Eastern Test Range are among the most sensitive in the world. This 85-foot antenna can receive telemetry signals from space vehicles over 4 million miles away. As launch time approaches, with all systems checked out and the missile fully fueled, the Titan 3C is ready for flight. In the vertical integration building about 2 miles from the pad, launch operations are being conducted from the Launch Control Center. From here, The orderly countdown of the missile's pre-launch tasks is directed by the test conductor. Every detail of the launch vehicle systems, the payload, and continuity of all electrical connections are confirmed as operational during the long countdown. At the Range Control Center, the RSO conducts the countdown that establishes the readiness of the range to support the launch. The Range Safety Officer is the direct representative of the commander during the launch phase. He is therefore responsible to ensure that all launch operations concerning safety have been accomplished prior to liftoff, or he will not permit the launch to take place. All key areas are incorporated into his countdown, and through a series of questions and responses, he receives, through his vast communications net, the go condition of the entire range. The RSO makes an early call to sea surveillance. Concern now is for those who may have strayed into the ocean areas immediately below the missile's flight path. Helicopters, equipped with radios and bullhorns, patrol out to 20 miles. Up to the 3-mile limit, Coast Guard cutters intercept vessels which may have entered the danger area and direct them to a safer course. From radars as well as these visual sources, information about intruding ships is received and locations plotted. The pad safety supervisor responding to the RSO's call reports on the state of the missile destruct system and that the land launch danger area is clear. This means that all people have been evacuated and that the impact convoy is standing by, ready to control the area in case of disaster. The RSO punches up command control. He reports on the status of all command antennas, the high-power command system, radiating and ready to support, the low-power command system, standing by, condition go, and all downrange command antennas, such as at Grand Bahama, checked out and ready. Frequency control and analysis reports directly to the RSO. He confirms no radio interference on command frequency. FCA is go. CADAC, or Central Analog Data Distribution and Control, immediately behind the RSO, confirms the plotting boards are checked and calibrated, and the computer theoretical trajectory correlates. The Range Safety Officer rings the SRO. The Superintendent of Range Operations declares all range safety instrumentation, such as radars and telemetry, are operational and go. He confirms critical items, and that he will hold, meaning prevent launch, should any range safety mandatory instrumentation drop out prior to liftoff. This could include a signal transponder, a critical radar, or the impact predictor. During the last few minutes, the launch test conductor at the Vertical Integration Building receives the word that all missile systems are go and the final countdown is underway. Every effort has been made to make this a perfect launch. In the Range Control Center, the Range Safety Officer is completing the range support countdown. He is ready to contend with the ever-present possibility that the launch might be less than perfect.
This is the RSO for a final communications check. Parish 3.
Parish 3.
Parish 7.
7.
Parish 91.
91.
Wire. Wire. Radar. Radar. Telemetry.
TM.
T-minus 50 seconds.
SRO.
What's the range instrumentation status, please?
018 is skin only, heading at T plus 18 seconds. All other instrumentation is go.
Roger, copy 018
40
status.
seconds.
Unless you have a further change, you have a final clearance to launch.
Roger, understand. Final clearance to launch.
Okay, you get enable, local disable. Roger that. Command
T-minus
carrier
30
covers
seconds.
off. Switch covers up. We're at T-minus 25 seconds and counting.
TM reports AGCs are
T-minus 20 seconds.
Roger TM, understand AGC is green.
T-minus
T-minus
15
15
seconds.
seconds and counting.
Stand by for terminal count.
Okay, down, stand by, first motion.
10,
Roger
9,
that.
8, 7, 6, 5, 4, 3, 2, 1, 0. Ignition confirmed.
Wire ignition.
Roger, wire.
Wire liftoff.
Roger, wire.
TM has changed pressure.
Roger, TM.
Plus 10 seconds. Mark. Climbing the wire.
Roger, wire.
Wire is green.
Roger, wire. The VPs are moving up. Right, VP's green. You got first motion.
Plus 20 seconds. Mark. Wire is green.
Roger, wire. Understanding green.
TM green.
Roger, TM.
Wire programming downrange.
Roger, wire.
Plus
TM
30
confirms
seconds.
we're going
Mark.
downrange.
Plus
VPs are green,
40
and I'm
seconds.
picking up an alternate
Mark.
IP on the nominal. I have an IP on the primary, pass 1. Primary IP looks good. It's right on the
Plus
nominal.
50
At this time,
seconds.
we're plotting
Mark.
116 on the beacon.
TM green.
Roger, TM. Understand green. The VPs
Plus
are
60
good.
seconds.
Paralleling the nominal off,
Mark.
maybe a 16th of an inch. We're about to go off the board in maybe another 5 seconds or so. We're picking up pass 2 now on the primary
Plus
IP. It looks
70
like we have
seconds.
1918
Mark.
beacon. Roger, I got the 116 beacon and right on the nominal, and radar's on, going slightly high on board 1. Roger that. Okay, now we're 1 second off, 1 second slow. That sounds good.
Carrier on station 3.
Plus
Roger,
100
station 3,
seconds.
carrier on.
Mark.
TM, we're coming up on stage 1 ignition.
Roger, TM.
Plus 110 seconds. Mark.
Stage 1 ignition.
Roger, TM.
Okay, I got the 018 beacon right on the nominal. My board is showing high on the radar, but my second board showing right on. I believe I've got a bias in the first board. That's
Roger.
good.
We should have SRM jettison.
Plus 130 seconds. Mark.
Jettison, solid rocket motor cases.
Roger that. We have 1918 beacon
Plus
on
140
the
seconds.
second pass of the primary IP. Pass 3 is moving out now. It's right on the nominal. Everything looks good.
Radar green, IP, alternate IP, nominal.
Plus 250
Looks good.
seconds.
We have
Mark.
about 10 seconds to stage 1 separation.
Stage
Plus
1 is carrying off.
260 seconds.
Roger, TM.
Mark.
Stage 1 separation. Stage 2 ignition.
Roger, TM.
Carrier on station 91.
Roger, 91.
Station 7 carrier off.
Roger, 7.
Plus
We're at
460
416.
seconds.
Mark.
Mark.
IP's moving out now.
Stage 2 is cut off.
Roger, TM.
Plus 470
right on
seconds.
down.
Looks like we're going to make an orbit. We're through the gate.
The importance we place on safety is measured by the efforts underlined in this picture. During 20 years of missile testing at the Eastern Test Range, we have supported over 1,800 major launches without a single casualty. This, I believe, we can attribute to our stringent range safety procedures. The knowledge gained through our increasing experience will mean a future with even fewer missile malfunctions. Notwithstanding, the Air Force Eastern Test Range is committed to provide continued evaluation of missile performance, with range safety serving as a shield against potential disaster.